Hello, statistics students. Today we're going to learn about binomial experiments and binomial probability. Very interesting topic, fun to work with when it comes to probabilities. So, as I always say, let's get started. So there are 4 conditions that have to be met before we have a binomial experiment or a binomial setting. And these are listed on page 201 of your book. In many books, this and this are considered 2 requirements, then this and this. So we always say there are 4 conditions for a binomial experiment. This book combined these 2 and then kind of sort of created this 4th one out of thin air. But anyway, you have a fixed number of independent trials. And there are only 2 outcomes, success and failure, and the probability of success is the same for each trial. So let's come up with a situation that will help you remember these. I'm going to roll a die. I'm going to roll a die 10 times, and I'm going to consider rolling a 5 success. So 1, 2, 3, 4, and 6 are going to be failures. I have a fixed number of trials. I said I'm going to roll the die 10 times. Each die roll is independent. It doesn't matter what I got last time. This roll is independent. There are only 2 outcomes, 5 and not 5. And the probability of success is the same for each trial. It's 1 out of 6. Probability of getting 5 is 1 out of 6. And then my random variable x, if you go by our book where these 2 are the same, which we will, the random variable x counts the number of successful trials out of 10. So now we're going to come up with what is the probability that I would get exactly 1 5 out of 10, 2 5s, 3 5s, etc. If these conditions are met, then we can determine the probabilities quite easily. More simply, though, we can flip a coin 10 times. And the reason I go with rolling a die instead of flipping a coin is the probability of success is the same each time. If we're saying heads is our success, it's 1/2. Some people confuse that to mean that heads and tails must, the probability of success and the probability of failure must be the same, like they are with a coin flip. And that's not true. In a binomial setting, the probability of success has to be the same each time. If you're rolling a die and trying to get a 5, the probability of success is 1 out of 6. The probability of failure is 5 out of 6. Success and failure don't have to be the same. What matters is each time you roll the die, the probability of success has to be the same. It so happens that success and failure are the same when you're flipping coins. So here, flipping a coin 10 times is definitely an example of a binomial experiment. Rolling a die 5 times, if we wanted to know the probability of getting exactly 2 6s, well, I have a fixed number of trials. They are independent. My 2 outcomes are 6 or not 6. And the probability of success is the same each time. And I'm going to let my random number or my random variable x record the number of 6s rolled, the number of successes. So these are binomial experiments. So let's do this one. I've already got it all written out, but I'll cover some of the answers. So let's say I want to roll a die 5 times and I want to get 2 6s. So I get a 6 on my first roll, a 6 on the second roll, not a 6, not a 6, not a 6 on the 3rd through the 5th rolls. Well, the probability of getting a 6 is 1 out of 6. Probability of getting a 6 is 1 out of 6. And there's a 5/6 chance of failure, getting not a 6. So that probability, when they're independent, so you could just multiply them together. And That comes out to be 5 to the third over 6 to the fifth, which is less than 2%. So my first question is this the only way to get 2 6s? Is to get a 6, and then not a 6, not a 6, not a 6. Well, clearly that answer is no. What if I got a 6 here and a 6 here? Well, let's see. How many ways are there of getting 2 6s? Well, let's see. I could get 2 6s here, 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 and here. So what was that, 10? Think so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 ways of getting 2 6s, which turns out to be 5 choose 2. I have 5 spaces, choose any 2 of them. It doesn't matter if I get this one first and then this one, or this one first, then this one. Those would be my 6s. So there are 5 choose 2 ways of getting that. Now the next question is, does getting a 6 on one roll influence the probability of getting a 6 on a later roll? And the answer is no. So they are independent of each other. And what do we know about events that are independent of each other? That's coming up. Is the probability of getting a 6 each of those 10 ways the same? And sure, if my 6s are here and here, then it would be 1 6, 5 6, 5 6, 1 6, 5 6. It's always going to be, if I want 2 6s, it's always going to be 1 6 to the second power and 5 6 to the third power. And then, can I get a 6 here and here and a 6 here and here at the same time? And the answer is no. So obviously, each of those 10 times are mutually exclusive. You can't get this and this at the same time. So all of those questions lead me to this. The probability of getting exactly 2 6s is, well, I could get my 2 6s here, or I get my 2 6s here, or I can get my 2 6s here. And I go all the way up to the my last 2 dice being the 2 6s. Now the probability of A or B, or both, is the probability of A plus the probability of B minus the overlap. But we just said there is no low overlap because they're mutually exclusive. So we're going to add all these probabilities together. But they're all the same probability. How many of those are we going to add? We're going to add 5 choose 2 of them, which is 10. So this times 10, where it gives us the ability to add all those probabilities together, and that's going to give us our binomial probability. Stand by, uno momento. All right, had a visitor from another teacher for a moment, back in class. So what we've done here is we've used all of those rules that we've learned about as far as independent events and mutually exclusive events. And by having those 4 conditions that we did, we were able to use all these rules. That's why I asked these questions. That led us to this. So the probability of rolling a die 10 times, the probability of getting 2 6s is 16%. Now, what we really did there is through an example, we kind of sort of got an intuition for the binomial probability formula. This is going to look scary. Don't panic. I assure you, in a few minutes, you'll get it. Oh! Okay. So this is the binomial probability formula. Don't start writing it down. Listen first. Then after I've explained it and you know what you're doing, then pause the video and write this down. So the probability that x equals k, x is our random variable. So that was the one where I said, what is the probability that my random variable, which was measuring the number of sixes, equals 2? So x is my random variable, k is the number of successes that I'm trying to measure. In that case, successes was rolling a 6. Is n choose k, so n is the number of trials, k is the number of successes, and remember that came from adding all those different ways of getting the exact same outcome, you know, 2 6s. So we just, rather than adding them all together, we just multiply by how many there are. So it's n choose k. N is the number of trials, k is the number of successes. P is the probability of success raised to the number of successes. If P is the probability of success, then 1 minus P must be the probability of failure. Some books call it Q. I'm just going to leave it as 1 minus P. It's the same thing. And then N minus K, well, if I have N trials and K of them are successes, then N minus K must be the number of failures. So let's try it again. The probability that I get K successes in a binomial experiment is N choose K times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. That's what that formula is telling you. Now, K must be a whole number because it's the number of successes. You can't get 2.5 successes. And it's got to be a number between 0 and n inclusive. You might get 0 successes, or all of your successes, or all of your trials might be successes. So now you can pause, write that down. So let's roll 5 dice, and we're going to call getting a success a 6. So if we're going to let, that means now we're going to come up with the probability. What's the probability that if we roll 5 dice, we get 0 successes, 0 6s? Well, if you substitute the appropriate numbers into the calculator, you get a probability of 0.402. Because that's really just 5 choose 0, which is always, anything choose 0 is 1. It's the first number in the row on Pascal's triangle. It's always a 1. Probability of success raised to the number of successes, well, that would be 1/6 raised to the 0, which is 1, times the probability of failure raised to the number of failures. Well, if we're rolling 5 dice, we get no successes, that would be 5. So it's just 5 6 to the 5th, 0.402. Similarly, if you run the numbers for k equals 1, you're also going to get a 0.402. Please run these numbers and make sure that you get what I do. Make sure that you can enter these numbers into your calculator and get the same binomial probability that I do. Now, the probability of getting all 5 dice to be 6s is just going to end up being 1/6 times 1/6 times 1/6 times 1/6 times 1/6 times 1 times 1. And that's 0.000. It's going to be a very small probability. Anyway, you add these up. Because this is a probability distribution function, the probabilities have to add up to 1. And these are and this is the entire sample space. Here are the only number of outcomes you could get. You get 0 successes, 1, 2, 3, 4, and 5. If you have 5 trials, if we were to graph this, you'll always have 6 rectangles because you have to have a rectangle for 0 successes and then 1, 2, 3, 4, or 5 successes. A lot of people forget that 0. It is possible to lose at everything. I wouldn't know about that. So if we were to graph that binomial distribution that we were just looking at, probability of 0 successes is about 40.2%. Getting 1 success was 40.2%. 2 successes was down to 16.1, then 3%. 4% was 0.003, so 0.3%, and then 5 successes was, so close to 0. Now it makes sense. What's the probability that, let's see, if you roll a die, what's the probability of success? 1 out of 6. So on average, you would expect 1/6 of these 5 rolls, which is 5, 6. So somewhere between 0 and 1 would be the most common numbers of 6s you'd get. And that's why 0 and 1 are the 2 high bars. So if you have a binomial distribution, the expected value or the mean is usually like in the high bar or somewhere in between the 2 high bars, and we'll talk about that in class. In general, a binomial distribution goes up, reaches a peak, and then trails off, and it's usually not symmetrical unless it would only be symmetrical if the probability of success and failure are the same. So here we have 0. Here's the probability of 0 successes, 1 success, 2 successes, and then I put a gap in here all the way up to, if we have n trials, it is possible that they're all n of them would be successful. Not likely, but possible. So we will go over example 2 on page 203 in class. And there's also a table, Appendix B, page A8 of our current textbook. We'll go over how to read that. That's so that you don't have to run the calculations. It just says, if you know what the probability of success is, you know the number of trials, and you know the number of successes that you're looking for, it'll give you the probability. So we have a couple of things to go over in actual class. So let's continue. Those are, that was a discrete probability distribution function, by the way, was that, that little graph showing you all the possible outcomes of your experiment, 0 successes, 1 success, 2 successes, all the way up to n successes, and then assigning a probability to each of those outcomes. So page 209 shows us how to find the mean, variance, and standard dev of a binomial distribution. I just kind of showed you or gave you the formula, although you might not have caught it, how to find the mean. We'll just zoom in on our book here. The mean mu, or the expected value of a binomial, is n times p, number of trials times the probability of success. So that was when I said, well, if you have 5 trials and your probability of success is 1 out of 6, then you should expect 5/6 of a success, which was going to be somewhere between 0 and 1, and that's why those had the high rectangles. Variation, that's a big FRL, should be variance. And the variance is just n times p times 1 minus p. And the standard dev, we will take the square root of that. Now we do have, there is a website, we have a lab coming up. This one's a little more fun, it's more games. And it's what I call the Plinko Lab. Everyone seems to enjoy this one each year. But we will go to the Plinko website and we'll play some Plinko, and you will see that the outcome of Plinko is a binomial distribution, which means Plinko is a binomial experiment, which means it needs to meet those 4 requirements. And so we'll look at that as part of the lab. So let's say that in a binomial experiment, we're going to do 10 trials and the probability of success is 0.7. So 0.7 times 10 is 7. So the 7 should be the highest rectangle on our distribution, and it'll trail off down to 0 successes or down to 10 successes. So what is the probability of getting exactly 7 successes? Well, it's the most likely outcome. So it'd be 10 choose 7 times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So that height is about 27%. Now you might say, well, why do we even calculate a standard dev? But we could. No, actually, we're not going to do that. Didn't even read my own note. So we're going to stick to this right now. Sorry about that. So ignore the 68% for now. So the probability of getting exactly 7 successes, if the probability of success is 0.7, is only 27%. So my next question is, now let's multiply this by 1,000. I'm sorry, by 100. So now I'm going to do 1,000 trials, and I want to get exactly 700 successes. So now that I have 1,000 trials, the mean is 700, is the probability that I get exactly 700 successes, is it still 27%? And the answer is, it's not even close. So take a look. Now we can look at the green. The standard dev is approximately 1.45. So I go from 6 over to 1.45, then over to the 8, and over 1.45. So if this is normally distributed, approximately 68% of our data will fall in the 6, 7, and 8 rectangles. But my standard dev here is 14.5. So 16% of my data is going to fall in about 29 rectangles, 14.5 to the left and 14.5 to the right. What ends up happening is 700 is the highest rectangle, but because that's mu equals n times p. But if I go to the the one standard dev mark, I'm going to have 14.5 rectangles over here and 14.5 rectangles over here. Remember, all of your rectangles have to add up to 1. So now I've got, how many rectangles am I going to have here? I've got n is 1,000 trials. I'm going to have 1,001 rectangles going from 0 up to 1,000. And I can superimpose a normal curve on this where it's centered under certain conditions, and we'll talk about those. But the bottom line is, when I only had 11 rectangles, yeah, this one could be 27% tall. But now I have 1,001 rectangles. This one isn't going to be 27% tall. Because think about it. Wouldn't you say that 699, 700, or 701, they're all pretty much equally as likely? Yeah, this is going to be the most likely, but would you really bet your life? No, you could just as easily get a 699 or a 701. So that probabilities where they all have to add up to 1, those have to be spread out over 1,001 rectangles now. So that's not going to work. So the probability of getting 700 out of 1,000 is nowhere near the same as the probability of getting 7 successes out of 10. Okay, I was gonna talk a little bit about the Monty Hall simulation, which is part of your lab. I think I'll save that for a later video. So what I want you to get out of today is binomial probability, and that is if your experiment, which again, an experiment is just something you do to generate data. If your experiment meets those 4 requirements, then it is a binomial experiment. And you can use the binomial probability formula to determine the probability of getting K successes. So that's all I have for you in this video. Have a great day.